Hello everyone, my name is Scott Grizzard. This is Quiz 9B Review, Calculus, Fall 2020, University of South Florida. Okay, so if you want to watch me go through them while I write, that's the 11 a.m. I'm going to try to do this, not that I want to stamp on your questions. So if you have questions, by all means ask them. But of course I'm not writing because I already wrote the thing out. For most of these. So if you have questions, by all means stop. I don't want to move quickly. I just don't want to write everything again and take up the time to do the writing, which has its own value, but it's, you can watch the video if you want to watch me write them. Otherwise, I'm just going to explain them. Oop. For some reason, the tablet is not up. The tablet just disconnected. I don't know why. That's annoying. Okay, so the whole network just went kaplooey. Okay, well, now it's working. All right, weird. Anyway, so Daffy is wrong. And the correct derivative is -1 over the square root of 1 minus x squared. So now I'm going to prove it. So here's my intro. I want to show that dy over dx equals -1 over the square root of 1 minus x squared. And what I'm going to do is I'm going to let y equal arc cosine of x. Take the cosine star of both sides. Take the derivative of both sides and then use the triangle trick to rewrite the right in terms of x. And that's a weird kind of x. I want a nice little x there. All right, so how do we feel about that intro 1 to 5? That's what I wrote. Your result may vary. So let's see if I can type today. Okay. People are apparently having trouble seeing me. I've got disk space, average time, FPS. That's not interesting. Okay. So according to my little doohickey here, my upload bitrate is fine. So is anyone else having the issue? Okay. So I'm going to assume it's something to do with your internet. Twitch seems to work better. If you want to watch me on Twitch instead of trying to watch me on Blackboard Collaborate Ultra. So anyway, that's the idea of the intro. That 1 to 5. So just a few sentences, mostly in English, saying what I want to do. Okay. Now for my body, what I'm going to do is this. And this is a little messy, especially this fact that I did the triangle trick here on the right. So I'm going to let y equal arc cosine. Cosine equals cosine of y equals x, cosine star of y. And I have this little detail, since cosine star is the inverse of arc cosine. Do you need that little detail? You need some detail. You need a sufficient level of detail. So you need sufficient detail, and this is one way, this is part of the way to get sufficient, right? So do you have to have that particular detail? No, but you need a couple of these details, a few of them. Like the fact that I wrote chain here is another one of those details that kind of counts to having enough detail. You know what I mean? So the derivative of cosine, I take the derivative of both sides here. And I have a little chain here, and I wind up with negative sine of y times dy over dx equal 1. I solve for this, and I wind up with and here's another little detail here. I wind up with y in 0 pi, right? Because that's I lost the endpoints, and that's kind of the image. That's where this cosine star stuff is valid. All right, so I wind up with this bit here. Negative 1. Let me do this here. So I wind up with negative 1 over sine of y. How do we feel about getting 1 to 5? How do we feel about starting here? From the beginning. It's not letting me move the thing right now. How do we feel about getting from the beginning just to this negative 1 over sine of y, 1 to 5? From y equals arc cosine to dy over dx equals negative 1 over sine of y. 1 to 5 on that particular bit. Okay. Okay. Now I'm going to use this kind of triangle trick, and it doesn't look neat, all right? So, if I was writing this for a more advanced class, I'd probably be in trouble, and I'd have to kind of do a little bit more neatness here. But I'm going to do this little triangle trick, and I'm going to know I have cosine of y, and I want sine of y. Cosine of y is x, which is adjacent over hypotenuse, right? This should really be, I have x equals this. That didn't work. Yeah, that really didn't work. Fine. So I have this x business, which equals the cosine of y, which equals, it's really cosine star of y, which equals the adjacent over the hypotenuse. And what I want is the what I want here is to get rid of something with sine. Okay. So I have cosine of y here. I do adjacent x equals adjacent over hypotenuse. So wouldn't it be nice if the hypotenuse here was 1? Wouldn't it be nice if the hypotenuse was 1 so I could divide by 1 and be happy? I don't know. I did it much better in the 11 a.m. Wouldn't it be nice, right? A little Beach Boys there, right? Wouldn't it be nice if, if that hypotenuse was 1? All right, so what I'm going to do is I'm going to say, okay, well, let the hypotenuse be 1. That makes this adjacent side x, and that makes this opposing side y. So all I need to do is solve for the opposite. So I've got 1 squared equals x squared plus sine squared y, which gives me that sine squared y, I move the x over to this side, is 1 minus x squared. That gives me sine squared of y of 1 minus square root of 1 minus x squared. So I take that sine of y and I stick it back into that negative 1 bit there. So how do we feel about our little triangle there, 1 to 5? So this would be the triangle. Let's see, stop. And start. All right. And so I sub that back in there, and I kind of mentioned that I only need the positive side because this is another one of those details. Do you need it? No. But it does count to the total amount of detail. So if you need a little bit more detail, normally doing an introduction will take care of enough detail for you. But you want a few more details. There are the details. You just need to convince the person that you know what you're doing, and So then I get that, and then I kind of just write this last little statement. Thus, the derivative of arc cosine equals this, and I'm done. Again, you don't have to write that, but it's details. It's kind of nice. It kind of concludes. It makes it look like you knew what you were doing, which is kind of the point, right? I need to know what I'm doing. Now, so how do we feel about that whole proof there? Wonderful. I'm trying to make it so that it zooms out. There it goes. And now it wants to do this. I wonder if there's a way to tell it that when I hit the screen, I never, ever, 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 ever want you to pull up the thing. I don't know. My guess is it's sort of the thing. So the whole proof. So stop and then start. Okay. Now, it happens that if the triangle is not your thing, there's another way to do this. So if the triangle's not your thing, I can actually pull out this identity, this Pythagorean identity, and I could just swipe this in there, right? Since sine squared y plus cosine squared y equals 1, I've got that sine squared y, and I've got that the cosine equals x. So I've got that the sine squared of y plus the x squared equals 1. And that means that 1 minus x squared is equal to the sine squared. And I take the square root of both sides. Note. And then I kind of note here on the bottom. Note y is in 0 pi. So sine y is greater than 0. And I don't need anything. I don't need any fancy dancy stuff. Okay. So how do we feel about that kind of alternative? Right? There's an alternative. So I can use the identity. You don't have to. The triangle trick is actually a little bit more flexible. The triangle trick will do more. It won't really do more, but you can, depending on what you're doing, you can just, you can sometimes get a little more with the triangle trick, faster than you can dealing with the identities. So it's the same thing, except one is nice and picture, and the other one is, identity. Right? This is something you memorized. This is something you actually understood. Right? This is something you understand. This is something that you memorize and then do algebra on. Now, if you're the type of person who likes to memorize and do algebra, more power to you. You can do this. You can do it even if you aren't that type of person. You can just do it. If you want the others, right? So if you've got something with a cotan or a secant, or something like that. If you want the other, or tangent, if you want the other Pythagorean identities, this is just kind of a little side note. I can actually pull them off if I only have sine squared and cosine squared. So let me show you how that works. This is if you need the other ones for some reason. If you're going on to Calc 2, that reason is you're taking Calc 2. So from sine squared x plus cosine squared x equals 1. The question is, how did the cosine in the first identity, the cosine turned into x squared because cosine of y was x? Okay. Okay. So from sine squared, I can actually get the other identities. Get the others. Okay, so the first one I want is tangent, so I'll just divide through by I want the one involving tangent. I divide through by cosine. And, if you forget which one's which, just divide first by cosine and then try the sine one, and you'll find it eventually. Right, so I've got sine squared of x over sine of cosine squared of x plus cosine squared of x over cosine squared of x equals 1 over cosine squared of x. right? And then sine of a cosine is tangent plus 1 equals, and this is secant squared. For the other one, so that's the one with tangent and secant. Obviously, most people remember it tangent squared minus secant squared equals -1 or something like that. Or most people remember it secant squared minus tangent squared equals 1. Whatever. It's really this. And then the other one is sine squared of x. I'll divide through by sine this time. Cosine squared of x over sine squared of x equals 1 over sine squared of x. And this one is 1. That's cotangent. And this is cosecant. Okay, so how do we feel about the fact that if I want to use these, I only actually have to remember one of them. And the others just come by it. So identity, what do I want? Mnemonic. It's not really a mnemonic. It's the identity only need find the others. Right? It's not really a mnemonic. It's more than that. These are kind of proofy things, right? But I don't need to memorize all three of them. If I memorize the first one, and then I just remember, well, divide by sine squared. If that's not the one you want, divide by cosine squared. So it's kind of handy not to have to memorize them. They all just kind of flow from this one fact. And if you do the triangles, then, so the triangle for this one looks like this. Right, this is 1 here. So this is cosine of x, and this is sine of x, right? The northiness is that. For this one, when I'm done with it, this is going to be tangent. So I'm going to wind up with opposite over adjacent. So I put a 1 there, and then I wind up with secant as that length there. And then I do, if I do the other one, I wind up with a cotangent here, 1 there, and cosecant, if you want to know what they look like. I don't know why you want to know what they look like, but that's what they look like if you care. All right. But that's a nice little trick, right? When you get into Calc 2, you'll appreciate the fact that you can convert those. Because Calc 2 has these antiderivatives, which, you need these kind of identities hanging around. Okay. This little limit problem here. I kind of just want to put... this is kind of the equals thing, right? So these are kind of equals. I'm just going to sub in the infinity. And there's a little note here to do. If this is like, I can do this trick because arctan is continuous on its domain. Okay? So arctan, in particular, it's continuous near infinity. Okay? On one side, right? So I've got a kind of one-sided type, right? Negative, I'm not doing negative infinity, right? Near infinity, it's it's continuous, if that makes sense. I can't do this trick with tangent. Well, first of all, the tangent of infinity, the limit as tangent goes to infinity is not defined. But even here, where I've got I kind of have to say, it's not, tan star is continuous. By all means, if someone wants to ask a question and their user handle is user temporarily suspended, which is making me somewhat suspicious. So I may regret saying yes and doing that. But okay, go ahead. So I need to make sure it's continuous, right? But this is continuous. But tan is continuous. Is continuous near 0. So that's just kind of a note. Okay. Is there any thoughts about that? So that's just a little thought to keep in the back of your mind. This trick only works when I'm dealing with things that are continuous around what I want to talk about. Anyway, that's a major distractor that I'm putting up for. I just wanted to kind of mention it. Now, here I've got like arctan of infinity. Okay, arctan of infinity. It's pi over 2 or it's pi over 2 plus, right? So here's the happy place for arctan, right? Is everyone on board with that being the happy place for arctan? 1 to 5, how do we feel about the happy place of arctan? I'm sorry, the happy place of tan. Okay, so the point is that the happiness of tan, the happiness of tangent is kind of the thing I want to think about. And so what I want to do is I want to take, I want to take my, right, as I come over here, the tangent line. If you think about this length of the tangent becoming infinity, and remember that the length of the tangent is the length of the point to this x-axis. So I kind of just go off and go off and go off and go off like this, right? And as I approach pi over 2 from the positive side, tangent goes to infinity. So arctan, as arctan goes to infinity, as arctan, as x goes to infinity, arctan of x is going to go to pi over 2 from the right. All right? How do we kind of feel about that 1 to 5? So, limit as arctan to limit as x to infinity arc. I'm putting \2 as if you know what that means. As arctan to as x to infinity, arctan of x to pi over 2, and it's really pi over 2 right. So how do we feel about that 1 to 5? What person, past, present, would you invite to speak? What kind of question you'd ask? I think we'd invite Dean Martin, and we'd ask him to prove the intermediate value theorem. Okay. All right. So I don't know if any of these would show up on the test, but given her love of limits, limit problems, I'm going to go ahead and say maybe. In a very authoritative maybe. So someone asked me that earlier. Is this going to be on the test? I have no idea. But it's apparently fair game, so I'm just going to, say it's fair game. Okay, so let's move on with life. This is a throwback. This problem, I'm going to say it before, I've said it again. This thing is very important. This function describes a lot of stuff. So we kind of want to have it around. We kind of want to be able to take its derivative quickly. In fact, by the time we're done, you should have, by the time this course is finished, when someone asks you to derive x to e to the negative x, you should have coming out of your mouth should be e to the negative x times 1 minus x, and you should just have it in your brain f prime of x equals, it should just kind of just flow, right? And that'd be horrible if you wrote it on a test, because you'd be showing no work. But by the time we're done, this should be one of those things that someone asks you x times e to the negative x. You should just like be that. So how do we feel about this one, 1 to 5? Okay. One day I'm going to do a comedy routine about teaching online, and that Dean Martin question's going to come in there, right? Someone asked me, who would I invite? Okay. So if you're not comfortable with that derivative, come see me. Let's talk about it. Let's get comfortable, because that's kind of a thing. All right, so let's do this next one. Now, people have been asking me, do I have to... Okay, so if you get arctan in a derivative problem where it doesn't say prove the arctan, derive the formula for the derivative of the arctan, right? If it says derive the formula for the derivative of the arctan, or it has a question like this, then you actually need to derive the formula. But if I get a question like this, right here, I can take the formula as given. All right? So 1 to 5, how do we feel about when I have to derive the formula? Right? I don't want you to think you always have to derive the formula. This is one that I can just stick out there, right? It's not asking me to prove the derivative of arctan or derive the derivative of derive arctan or figure out what the thing is and prove it or whatever. This is just asking me to use it. All right? This is a use it problem, not a make it happen problem. And by the way, when you get to your final exam, heck, when you get to your test, this is just a little thing. What you should write on your test. This is what I would do. Basically, for any calc test you ever take going forward. All right? So I would do this. F prime. And I would actually write them. Okay? So if f is this, that's what f prime is, right? So sine of x, cosine of x. Cosine of x, negative sine of x, ln of x, 1 over x. And I do, blah, 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 I do tangent. And I would do 1 over cosine squared of x. And I would also write secant squared of x here. Except I probably wouldn't do cotan unless I saw it. And then I would do arc sine of x, 1 over square root of 1 minus x squared, arc cosine of x, negative 1 over the square root of 1 minus x squared, and arc tan of x. 1 over 1 plus x squared. And the reason I would get into the habit of that is because then when you have to take antiderivatives, you already have your chart. Okay? So I'm just saying, as a technique for taking tests on 3 and then 4, you're going to need to do it on 4 no matter what, on the final, because you're going to be going backwards. But it's faster if you just write out a little cheat sheet for yourself on the cover of the test. It's not before the test starts, obviously, but as soon as the test starts, just go, and just have them. That's how I get through Calc 2, by the way, because, I didn't do well in Calc 1. It took me 2 tries to get through it. And then when it came to Calc 2, I still had to get through Calc 2. I was like, right, I got my little thing. So I got my little cheat sheet of derivatives and antiderivatives. And I dump. E to the x. Okay, I don't really need to remember that one. But I would just start doing that on tests. Anyway, what I've got here is I've got a chain rule right here, right? The journey of x this time is going to involve an x cubed, and then I've got an arctan of the thing. So I'm going to take d over du. I'm going to set up the chain. This is going to be my u, and I've got here, I'll just write down what my u was. U equals x cubed, and I'm going to do that. And then I'm going to do this step here, right? Now that I've got this, I'll put 1 over u squared plus 1 times the derivative in terms of x cubed. Now, here's where people mess up. So now this is baggage, and I'm moving on, and this is 3x squared. Now, people mess up, and I did it once when I did it the other way this morning. I actually messed this up, right? I forgot to do this too. All right, it's x cubed squared. I remember to do it the first time, but then when I did it the second time, I forgot. So this little bit of detail, everyone, especially if this was x squared, and that's a favorite thing. If a calculus instructor hates you and wants to be annoying, I of course don't, but I'm not writing the test. If a calculus instructor hates you, they're going to do arctan of x squared or arcsine of x squared. Because what's going to happen is you're going to do your u, you're going to see the square, and you're going to forget to square again. So when I sub this in, it's x cubed squared plus 1. Right? Because my u is x cubed. And on the test, your u may be x squared. So watch out. And I get that 3x squared. And then if I insist on simplifying, that's what it comes out to be. I wouldn't, but okay. So how do we feel about that problem 1 to 5? Okay. Yeah, there is another way to do C. So the other way I can do C is I can let y equal the arctan of x cubed. Then I take the tan star of both sides, and notice I'm going to skip some steps here, right? So now I'm going to take the derivative of both sides, but I'm skipping steps. So don't skip the steps that I'm skipping, because I was just moving through it. So then I'm going to get this, and then I wind up with this dy over dx equals 3x cubed because I took the derivative of that right-hand side. And then I wind up with 3x cubed times 1. Now, this cosine squared of y thing, I messed it up the first time too. So this is where I messed up. The hypotenuse squared is 1 squared plus x cubed squared. Okay. So this y business, the tangent of y is still x, right? That's where I'm sorry, the tangent of y is now x cubed. So when I throw in the square business, I need to remember to square it. And I forgot it the first time. So the hypotenuse equals 1 plus this x to the 6th. And then I take the square root, and that's where that x to the 6th comes in. And it's very easy to forget to do that. Okay? And then this is where you get this bit, and then it becomes this bit, and everything's together. So you can do it that way. But if you want to do it on this one, that way is annoying. And let me show you what I mean here. Right? So here's the regular way to do it. you take the derivative of x squared times arc sine of x, right? This is a product on the outside, so it's just that. And then I carry baggage. Make sure when you carry your baggage, you're careful. The first time I did it, I wrote arc cosine here. I wasn't taking the derivative. I just didn't carry my baggage correctly. So I got 2x arc sine of x plus x squared times 1 over the square root of 1 minus x squared. How do we feel about that 1 to 5? This is 2d. And in a sense, this other way of doing it, like the way I did 2c, it actually shows you understand even more, right? Not only do you understand where arctan was, you actually understood where it came from. That's actually, in one sense, a better answer in the sense that it shows that you know more, right? You're flexible on this. You actually understand something. But if you've got products with these things, this trick of doing that becomes a real pain in the neck. And let me show you what I mean here. I promised during the 11 that I would do this on the 5, during the 5, so I'm going to do it. Okay, so if I set this up, y equals x squared arc sine of x, I wind up with y over x squared equals arc sine of x. All right. Then when I take the sine of both sides, I wind up with sine star of y over x squared equals x. So now I've got a quotient inside a chain. Yuck. Okay. And if I do it with the -1 trick for the inside, I'm going to have a quotient. I'm going to have a chain inside a product inside a chain. So, you know, it's unpleasant. Well, let's do it. So this is my u. So I'm going to let my u. This is all messy. I'll rewrite this. So now when I do it, I'm going to have a chain. So I'm going to have sine of d over dx is sine of y over x squared. That just became a u. All right, so u is going to equal y over x squared. Equals d over dx of x. That's going to be nice. Okay, so now what I get is the derivative with respect to u, d over du of sine of u times du over dx, or d over dx of u, either way, equals 1. Excuse me. Excuse me. All right, now I'm going to do this, and I'm going to wind up here with, let's see, I'm going to wind up here with cosine of u times d over dx of y over x squared equals 1. Well, now I've got a quotient. So now I've got cosine of u times and it's going to even be worse because I'm going to wind up with a y over x squared inside the angle. And it's not going to be pleasant at all. So if I try to do this, I'm going to wind up with this. I'm going to wind up with the first, the derivative of the first. So this is going to be dy over dx times the bottom minus the derivative of the top times the derivative of the bottom times the top all over the bottom squared. Yeah. And then when I sub that back in, I wind up with the cosine of y over x squared times, is there any way for me to make this less unpleasant? There isn't. Dy over dx x squared minus 2xy times 1 over x to the fourth equals 1. Now from this bit, I'm going to take this x to the fourth, I'm going to scoot it over. And then I got to do the cosine of y, I got to put that down. So I'm going to wind up with cosine of y over x squared. Actually, I want that on that side too, don't I? So this is going to be dy over dx, x squared minus 2xy equals 1 over x to the fourth times cosine of y over x squared. Okay. And do I need to continue? Or is everyone now convinced that this is a bad idea? Is everyone now convinced that doing it this way is a bad idea? Right, I'm actually going to have to take the arc cosine of this somehow in order to get that out. And that's going to be very unpleasant. I'm going to need a trig identity to pull out that y. It's not going to be a good thing. Okay. I don't even remember the trig identities for pulling out quotients. Do you? Right. Right, so it's not that you don't have to remember the proof. You need to remember how to use. So the point is that you need to remember how to do. And if you forget, you can do the proof. The proof is very quick, but don't do the proof. Don't try to do the whole clunky thing. Just do the proof of the little bit you need. You know, do it on the side. What was the formula again? If you forget the formula, right? I forget formulas all the time. I rederive them. If you asked me what the derivative of arc, cotangent I can figure out pretty quick. If you asked me for the derivative of arc secant right now, I would not be able to tell you. Okay? No clue. I have a clue, but, you know, I'd actually have to sit down and figure it out. Right? I can do it, right? I do, you know, y equals arc secant of x, that means that the secant of y equals x, and then I get secant star. What was the domain again? I had to think about it. Right, I can, right? I convert this to 1 over cosine of y equals x, then I take the derivative. I can do this, right? I got a reciprocal rule here on the left. It's unpleasant, but I can. But the point is that, you know, unless I need to do that, since Calc 2, I've never used that formula, ever. I actually have used these, arc cosine, arc tan, arc sine. These I've used. I've never used one of the formulas for the other ones. So, yeah, you need to memorize these. You need them for Calc. You need the weird ones for Calc 2, because in Calc 2, you always wind up with these weird things that you have to integrate, and they turn out to be things like arc cosine, arc sine. This is especially true for ellipses. So when I want to do derivatives when I want to do antiderivatives of ellipses, when I want to do the area inside of an ellipse, or the area, you know, by some kind of curve like that, these are useful because I wind up using them. And even the others are useful for those, but I don't do those problems in real life. Right? I suppose if you're in physics, you are. All right. Any other question? I'm talking way too much. Sorry about that. So yeah, so implicit differentiation is kind of the thing that makes this work, right? So, and as I said before, all these tests are cumulative by their very nature, right? I need to remember how to do the product rule in order to, keep going in the class. So the implicit differentiation bit is this right here. So yes, you need to remember those things. Okay. I talked way too much. Sorry about that. Any other questions? Okay. So I'm going to stop streaming here. Let's talk about the problem set.